All right, so we're going to go ahead and get started on supporting connective tissue. This is a subgroup of connective tissue, and it's going to look at what is both cartilage and then bone. So the first one we start with is cartilage. Remember that cartilage is going to be found at the ends of all long bones. It's going to be found usually between bones to help as a cushion between the bones so that when they come into contact with each other, that we're not doing damage to the bones. It has a very jelly-like matrix. Remember that the matrix is the fibers and the fluid. About 80% of all cartilage is fluid, and that all cartilage in the body is avascular, meaning that it has no blood vessels. Because it has no blood vessels, cartilage usually does not heal at all. It's used as mainly for protection. So we look at that for all cartilage, and we have three different types of cartilage. Remember that we're looking for the cells, the fibers, and the ground substance, the fluid. So we look at this interlocking network of fibers that help create this, what is a jelly-like substance. I think something that's a hard set jello, and that it is very resilient, meaning that it can take lots of small amounts of pressure and that it will usually bounce back to its normal shape and size. That when we look at what are the cells, that a very large component of the cells are the chondrocytes. Remember, chondro is cartilage, so chondrocytes are the cells that monitor cartilage. And that those chondrocytes are usually found inside of little caverns or chambers within the extracellular matrix, and that those caverns are called lacunae. Now, outside of almost all cartilage in the body, we have a perichondrium. Perichondrium is the outside dense irregular connective tissue that helps hold the cartilage together. If we damage the perichondrium, it almost always leads to damage to the cartilage, and so we want to make sure that we do not damage the perichondrium, the connective tissue on the outside that's holding the connective tissue that is cartilage on the inside. We look at that in our bodies, we have three different types of cartilage. Those three different types of cartilage are hyaline cartilage, fibrocartilage, and elastic cartilage. So just as a brief description, remember that fibrocartilage is found between the discs of your, they are the discs between the vertebrae and your back, and the pubic symphysis is fibrocartilage, where we hold the two pubic bones together. Hyaline cartilage is going to be the predominant portion of cartilage that is your nose. It's also what creates the hard structure of cartilage that is your ear. And it's also the cartilage that's found at the end of all long bones, what we call articular cartilage. That's hyaline cartilage. And then elastic cartilage, for most of us, is the very tip of our nose. And also your earlobe is elastic cartilage. Brief descriptions there. So the first one we look at is hyaline cartilage. And hyaline cartilage is fairly distinctive in that we look for the cells, the chondrocytes, and whether you're looking at the drawing in the middle or the histology slide to the right, you can kind of see what looks like fish eyes. The white outer edge with a dark nucleus in the center and then a dark ring around it. The dark ring is the hole, the lacunae. The actual clear piece and the center part is the individual chondrocyte inside the lacunae, and that's what creates what looks kind of like as fish eyes. Now, with hyaline cartilage, this is fairly distinctive in its color, in that usually it's going to be this silver blue tint to it, and that the hyaline cartilage itself, like I said, is found at the ends of all long bones, and it's there for a piece of reduction in friction and cushioning for the long bones. We also see it as the connection of your ribs to your sternum. That is the hyaline cartilage, what we call the costal cartilages. And we see that the hyaline cartilage is really strong because it has lots of fibers. That really kind of dark blue tint that you see on the outside of the chondrocytes, that's the fiber portion that we see. and that is the of the cartilage, that is the collagen fibers. Sorry about that, my brain took a little jump. So we look at the dark blue as being the collagen fibers. It's why hyaline cartilage is slightly stronger than elastic cartilage, because it has more of the collagen fibers. The second one we look at, which is fibrocartilage, is by far the strongest of the three cartilages. And when we look at fibrocartilage, whether you're looking at the drawing in the middle or you're looking at the histology slide to the right, you see many more fibers here and very few numbers of chondrocytes and very few groupings of the caverns or the lacunae. Because there's so many more fibers here, so many more groupings of collagen fibers, fibrocartilage is the strongest of the three cartilages. And if you think about between the vertebrae in your back and your pubic symphysis, we also see that there's a large quantity of fibrocartilage for the meniscus between your knee and in the shoulder. And this helps to create capsules and to create groupings of really, really strong cartilage that help resist lots of tension. If somebody tears out their knee, they almost always tear some of the fibrocartilage that is the meniscus in their knee. The last of the cartilages is called elastic cartilage. And if you remember to looking at the three fiber types, elastic or elastin fibers were the black to dark purple fibers. If you look at the histology slide to the right, you'll see that we don't see individual fibers here, but we see these large clumps of dark groupings around the lacunae. And for elastic cartilage, most elastic cartilage does have this red tint to it. So we have lots of collagen and lots of elastic fibers. These elastic fibers help to allow this cartilage to stretch and come back almost to its normal shape and size. So we'll see this as a portion of your auditory or eustachian tube, portions of your earlobe. It's also found when we look at portions of the back of the epiglottis that helps to cover over the trachea when we swallow food and or drink. Your elastic cartilage of your vocal cords. So this is why when individuals do lots of screaming or when they are singing at the top of their voice, they do damage to their vocal cords, because this is made of elastic cartilage. And it's not uncommon for singers who have damaged their voice severely to go in and have Botox injections into their vocal cords, because it will actually help tighten these up. All right, so the next components of cartilage that we look at are how cartilage actually grows and repairs itself. So when we look at the growth of cartilage, it actually is taking place in two different time periods of your lifespan. The first is called interstitial growth. The second is called appositional growth. So interstitial growth is when you are that embryo to fetus and we are creating new cartilage cells. This can take place into your early, we talk about being an infant child as interstitial growth. And so we'll see that the chondrocytes actually have the ability to divide. And as they divide, they help create what is the new matrix outside of them. And as this occurs, the cartilage actually gets bigger in size. We'll see this go through childhood, and by the time you hit puberty, interstitial growth is done. The second time period is appositional growth, and appositional growth starts in adolescence and goes through the rest of your lifespan. And appositional growth looks at now we have chondroblasts that are going to secrete a new matrix outside of the cell, and we're no longer increasing the number of cells, but we're actually increasing just the matrix outside of it by the chondroblasts creating new matrix. This then increases the width of the cartilage. All of you can see this when you look at pictures of your parents or your grandparents, and that their noses and or their ears get longer and longer and longer. And it's because the appositional growth of the cartilage is actually increasing in size. We're actually increasing the size of the tissue. Sorry about that last transition. This gives you a picture of what is interstitial growth and appositional growth. Interstitial growth shows you on top that we are taking an individual cell, a chondrocyte, and that inside of that lacunae that the chondrocyte actually replicates. And as it replicates, we create new matrix outside of it. Remember, the matrix is the fibers and the fluid. And so now we've increased the number of cells and we've increased the matrix. And so we get growth of the cartilage. Remember that interstitial growth occurs from embryo through adolescence, about the time we hit puberty. Appositional growth on the bottom takes place from puberty basically on through the rest of our life. And in this, you'll see that we're not increasing the number of cells, but actually what we're doing is we're increasing the amount of matrix outside of it, so the fluid and the fibers. And so we see that the individual chondroblasts come in and create new matrix, not the number of new cells. And so appositional growth is considered to be width growth of the cartilage. One of the conditions that we see quite often that is a genetic and inherited and a genetic malformation is Ehlers-Danlos syndrome. And it is inherited most likely when we look at it being passed down as a pure connective tissue disorder. This connective tissue disorder is the breakdown of cartilage. And so what we see is that the collagen fibers are actually created incorrectly and they're faulty. They don't work properly. And so for these individuals, their skin is usually very velvety to the touch. They can pull the skin a long ways away from the body. It's called hyperextensive skin. And that their skin is fairly fragile, meaning that it tears and will create pretty severe bruising very easily. Anytime we have damage done to the skin, it's almost always going to leave severe scarring, and that these individuals heal very slowly. And so if we look at surgeries or dislocations or damage done to the joints, we usually see major problems with these individuals, and a lot of times they'll have to have braces placed on their joints to help give them a little bit more stability. You'll notice that on the person's knees, little things that we would normally do as children where we fall on our knees and we cut ourselves and those, heal and go away. For this individual, it's created really, really nasty scarring on their knees. And then the person at the bottom, don't try this because you might dislocate your thumb, but this person's thumb joint is very, very hyperflexive, and so we see that the joint allows them to pull their thumb back to their forearm. Many of the individuals that have Ehlers-Danlos syndrome also have scoliosis. They usually have very weak or very poor muscle tone, and besides seeing these problems at the joints, we also see issues at the heart, and so we'll see that their mitral valve usually has problems. This takes place in about 1 in every 5,000 to 1 in every 10,000 live births. So it's not uncommon. We just look at that, how severe is it for each person. All right, so we are now done with cartilage and we move to bone. Bone is also considered to be a supporting connective tissue, meaning that it helps support the body. So when we look at bone, osseous tissue, we still have the 3 components. We're looking for the cells, the fibers, and the ground substance. The difference is for bone, there is little to no ground substance. And so mainly what we see here are the fibers and the cells. So we look at that all bone that is long bone is going to have a connective tissue on the outside, a dense irregular connective tissue. Just like we had the perichondrium for cartilage, we have the periosteum for bone. And when we look at bone tissue, we look at 2 different components to give us what we think is the strength and the hardness of bone. So the strength of your bone is from the number of collagen fibers we have. The hardness to your bone is the amount of calcium salts we have. Now remember earlier in the year I talked about that your body does not care about the amount of calcium in your bone. It only cares about the amount of calcium that's in your blood. So if you're not consuming good calcium every day, your bones will be broken down and the calcium salts will be removed from bone and put into blood. If you are eating good calcium every day, the excess calcium is then placed into bone and you end up with really hard bones, which is a good thing. So we had what were the chondrocytes for cartilage. We now have osteocytes for bone tissue. So this is a picture of bone. When we look at a picture of bone, this is actually of compact bone. And we see that there is a central canal. That central canal at the top of the page is where we would have the blood vessels and all the nerves that run through your bones. And then you're going to see the dark fibers. Those dark fibers are where we actually have in between them the individual collagen and the calcium salts. And we'll see the dark holes. The dark holes are the lacunae, the caverns inside of bone. And then the osteocytes will be inside the lacunae. So the dark hole is the lacunae. What's in the dark hole is the cell, the osteocyte. The last 3 slides that we have here today are with muscle tissue. As with bone, muscle has its own chapter, so we're just briefly talking about muscle. We have 3 different types of muscle: skeletal muscle, cardiac muscle, and smooth muscle. Remember that the main function of muscle is to provide movement. So when we look at the 3 different types of muscle and the movement that they cause, so skeletal muscle helps move the body, attached to bones, so that we have movement of the body. Cardiac muscle is for the movement of blood through the body. And smooth muscle is for the movement of something through a tube. So we think blood vessels and digestive system. And because that skeletal, cardiac, and smooth muscle all helps with movement, we then start looking at some of the secondary components. So when we look at skeletal muscle, it's also there to help with your basic posture and to produce heat. Every time a muscle in your body contracts, it produces heat. And so this is the 3 pictures and 3 histology slides of what is muscle. So at the top of the page, we have skeletal muscle. Middle of the page, we have cardiac. And at the bottom of the page, we have smooth muscle. If we look at skeletal and cardiac muscle, you'll see that they both are striated. You can see the dark and light lines that are in the drawing fairly well. And then in the histology slide, you can see the dark and light lines that are running vertical. Those dark and light lines are called the striations. It's actually where muscle contractions occur. And then you'll notice that on the outer edge of both cells that we have a nuclei, and that both groupings are multinucleated, meaning that each cell potentially has multiple nuclei. For skeletal muscle, cardiac muscle has 1 nucleus per cell. So when we look at skeletal muscle, one of the major differences we see is that skeletal muscle runs the full length of a muscle. So if we think about the large muscles in your leg, those individual cells run the full length of the muscle. And so that's one reason why they have to have multiple nuclei. Cardiac muscle, go ahead and make a fist. Your heart is roughly the shape of your fist. It wraps around. Cardiac muscle, still striated, but now because the heart is in a kind of an oblong or oval shape, individual cells run into each other. And so instead of being a single cell that would run the full length of the heart or all the way around the heart, these cells are shorter in size and they come into connections with each other. And where the 2 cells connect is called the intercalated disc. And that intercalated disc is where the signal from one cell goes to another to help cause a contraction. At the bottom of the page, we see smooth muscle. And smooth muscle, each individual cell has its own nucleus. And one of the things that is the most easiest to see with smooth muscle is that it's really hard to tell where one cell starts and another one stops. They kind of run into each other, and it's kind of a mismatch of cells. And remember I said this is going to be found anywhere that we have a tube. And so anytime that we stretch smooth muscle, it contracts. So as blood moves through your blood vessels, it pushes outward to stretch the arteries, and the arteries push back because the smooth muscle is contracting. This is the end of tissues 5.